got a hidden state denoted by S, and it can take values 0 or 1 or 2. And we've got an alphabet or a set of tokens that can take values A, B, and C. So to generate a sequence, we'll define an index L, and this is just bookkeeping. It tells us where we are in the sequence. I'm going to denote the Lth step and the Lth plus 1, or L plus 1th step. We'll have the hidden state S, and we'll have our token X. So let's say that the hidden state, the first hidden state at the L equals 0 index, comes out as 1. Well, we need to define what the prior probability is for that result. And so that's defined using the eta, where the argument here is the empty set because there are no tokens to condition on. And let's say, for example, it's got this probability mass function. So this is just the probability mass function for the 3 values of the hidden state. So we can write it out explicitly. It's just the probability that the 0 state is 0 for the first entry, the probability that the 0 state is 1, second entry, and probability that it's 2 is the third entry. So with this setup, the first value that gets generated is that first value for the hidden state. Consequently, after that, the next hidden state is generated and the token is generated. So the causality is a bit like this. Having seeded the first hidden state, the subsequent hidden state at the next L step, and the corresponding token is then generated. So let's say the next hidden state is also a 1, and that then causes the next token to also be A. We can interpret it causally like this. I like these sort of causal interpretations because it, I don't know, it just helps me understand things. So that's the kind of the causal sequence. In the paper, I remember that it was spoken about in the sense that the hidden state at step L gives rise to the joint pair of quantities, which is the hidden state at L plus 1 and the token at step L. I think it's quite, I don't know, I think it's harmless to look at it this way, where you can regard the the hidden state at step L giving rise to the hidden step at the subsequent step L plus 1, which then itself gives rise to the token at step L. So you would have a sequence something like this: S0, which is seeded using this prior probability, gives you S1, which then in turn gives you X0, S1 gives you S2, and S2 gives you S1, and so on. So that would be my causal interpretation. Anyway, so what we want to do, just getting back on topic, is to write down the matrices that define the dynamics for this system. So I'm going to denote this Lth hidden state as SL, and then the L plus 1 as SL plus 1, similarly for X. And the first matrix of interest is matrix A. The matrix A is the matrix that tells you about the transition probabilities between the hidden states. So it's the probability, and I'll explain I and J in a moment. It's the probability that you go to state J at the L plus 1th step, given that you're in state I at the Lth step. So it's purely concerned with the hidden state, and that's characteristic of traditional hidden Markov models. The matrix B is another interesting one, and it tells us about the tokens. So it is the probability of getting a token at step L conditioned on the hidden state at the subsequent step L plus 1, which I found a bit confusing at first, but it's when expressed in this causal language here, it suddenly made sense, which is why I just drew all this out. But essentially what this is revealing is the probability of getting a particular token at step L given the hidden state subsequently. So it's essentially saying the extent to which the hidden state reveals itself by virtue of the token it emits. That's how I think about it. And then we have the token labeled transition matrix Tx of I and j, and it is just the joint distribution of the token emitted at step L and the hidden state at step L plus 1. What do we want? J. Yeah, conditioned on the hidden state at the Lth step. And so this can actually be decomposed. So I'll just I'm going to number these pages before I lose track of everything. In fact, it might actually be worth talking about the dynamics a little bit first before I show that T is just the product of A and B, which is the result I was just about to go to. I think it might be worth just showing two examples. So let's look at matrix A. So if matrix A has large on-diagonal components, let's say 0.85, and I'm just thinking I need to normalize this, so whatever the final state is, whatever the final state is, it has to be one of the states 0, 1 and 2. So it's row stochastic, and we'll sum over j and normalize over j. So let's say values 0.05, 0.05, 0.85, 0.10. The numbers themselves here are not particularly interesting, but the point is that because the on-diagonal values are large, the hidden state S has a tendency to stick to its current value at each subsequent step. So let's say it starts at 1. There's an 85% chance it'll stay on 1, which is why you tend to get long, sort of sticky sequences like this with this particular matrix. So I don't know, maybe you'd get something like that. So the characteristic of this matrix A with the large on-diagonal values is this tendency to get these large substructures in the token, in the hidden states with similar subsequent, it doesn't move around very much. Basically, it's very sticky. And the matrix B has, as I said, it measures the extent to which each hidden state reveals itself through the token it emits. So let's say B has values, I don't know, 0.8, 0.8, 0.8, and I'm going to put 0.1 for the other ones. All this means is that if the system, the hidden state is in state 0, the token that gets emitted tends to be A with 80% probability. If it's in state 1, it tends to be B that gets emitted. Again, 80% probability, and so on. And so the matrices A and B determine the trajectories through these two state spaces of the sequence of hidden states S and the sequence of tokens X. And so the dynamics of the system are really enshrined in the parameters of A and B, as well as, I suppose, the prior probability which seeds the value of S in this first instance here. So you can imagine another example. Let's say A has large off-diagonal components and the on-diagonal elements are small. Well, that would mean that the hidden state tends to change a lot. And so depending on the values of the entries in B, that means that the tokens that get emitted might also change a lot. The values of B, as I say, reveals the correlations between the values of the hidden states and the tokens that get emitted. And so again, the dynamics of the system are enshrined in the values of the matrices A and B. So the reason why this is interesting is because this whole study is about discovering latent structure in these sequences of tokens by inferring what the hidden state is likely to be based on the tokens observed. And if the tokens that are emitted have a very particular structure to them, then it implies that that latent structure is there with regards the trajectories that the hidden states undergo And the whole point of really doing this study is to actually contrive the situation such that we have different values of A and B that correspond to the different Mess3 components. So in other words, we deliberately contrive these sequences so they have latent structure. And the question is, can the model detects that latent structure by inferring the hidden state on the basis of the token sequences it observes? And the way to go about it is to, well, firstly, let's actually say what we mean by the matrix T. So, actually, no, okay. I need to establish a slightly better notation, actually, before I proceed. So I mentioned that there are different Mess3 components, and I think, if I remember correctly, or at least the way I've been writing it down, I'm going to denote it with the variable C. So what I mean by C is, if C is equal to 0, then the matrices A and B have a certain set of values. Maybe they're sticky values like this. If C is equal to 1, then A and B have a bunch of different values. Maybe they're values that cause very frenetic, erratic sequences where the off-diagonal elements are large. So really C is just, it's the way of it's bookkeeping for which component we're talking about. Okay, so now what I can rewrite these conditions for A, B, and T that include the value of C. So by conditioning on the value of C, I'm now talking about which component we're talking about, but it doesn't really affect the probability theory that we need to go through in each individual case. So let's just go ahead and write it out again. I'm going to condition on that, but I'm now going to say that C takes a particular value. So in other words, by saying that C is equal to a particular value of C, that denotes the fact that we're talking about an A that has a particular set of values, characteristic values, if you like, of the latent, what's the word? Component is the right word. Okay, so I can write B in a similar way. So again, it's just the probability of getting the token X conditioned on the hidden state at the subsequent step, also conditioned on the component that we're talking about. And the matrix T, I'm going to put C in superscript here, and it's more or less the same thing. So we're looking at the probability of getting the joint distribution over the token at step L plus the hidden state at the subsequent step, conditioned on the hidden state, at the current step and on the component that we're talking about. Okay, so I need to do this quite carefully now. Realize that's out of frame. So I can write T by factorizing it carefully. I'm actually going to put C in superscript before the X there. So T of I and J is equal to this expression here, but I can factorize it. So I can write it as probability of getting this hidden state J conditioned on the previous, so the hidden state at the current step, along with C, multiplied by the probability of getting the token X at the current step, conditioned on the hidden state at the next step, also for component C. And if you look carefully, let's see if I've got it right. Yeah, so this first component here is just A. And I've got the indices J and I, so that's AIJ. And yeah, the second element here is B. So that's B of J and X, where I've got the indices J and X. And so T can actually just be written as the product of matrices A and B. the indices here might be slightly confusing. This is not an Einstein summation, so the J here doesn't get eliminated. It's just a direct element-wise product where every element of A at the position ij gets multiplied by the corresponding position in the matrix B at position ij. And now let me see if I can remember the next step. Yeah, it's escaped me, but I'll try and remember it. Oh yeah, yeah. So we want to marginalize now over all possible tokens. So what we can do is write that T where now I'm going to sum over all token labels, because remember this is the token labeled transition matrix. We can marginalize it and express the fact that Aij multiplied by, because here I'm marginalizing over x here, and A doesn't depend on x because it's got nothing to do with tokens. It's only got, that's the transition matrix for the transitions between the hidden states, but the matrix B does depend on tokens, and so this matrix B is inside this summation, and oops, and Bj of x, well, that just equals 1 because whatever token is emitted next, it has to be one of A, B, and C. And so when marginalized over x, this just equals 1. And we just recover the matrix Aij. In other words, the transitions between the hidden states are recovered. In other words, the traditional transition state matrix for a hidden Markov model is recovered when you marginalize over this token, this decomposition into different tokens, which has been done with these token labeled transition matrices T. Okay, I hope that's clear. Okay, so what? Well, let's recap where we are. So we've got L, our index, we've got S, and we've got X. And the point of this whole exercise is to try to use the tokens that we've got at our disposal in order to make a prediction as to what the latent state of the system is, the hidden state of the system. So let's say the system is in state, well, let's just fill out this table first. So I've got states SL, and then SL plus 1, and I'll have tokens XL, XL plus 1. The thing I really want to know is, given a set of tokens, let's say I've got tokens 0 to L, can I predict what state the system is in the subsequent step? That's really the object of interest here. And so we can write that down as a variable called eta. And you'll notice that I used eta before. And it'll start to make sense now why I used the empty set notation before when there were no tokens, because now I'm going to write eta conditioned on the set of tokens from the L equals 0 token all the way up to the L equals, well, the L equals L token. And so I'm going to denote that set of tokens as using this 0 colon L notation. And just like the prior probability vector, it has an index j because there are 3, it's a vector, it's a probability mass function over the hidden state. But it's now conditioned on these tokens, which are the data that we've used to inform that prediction. And so we can write it as the posterior probability of the hidden state at L plus 1. I'm going to say it's equal to j, corresponding to the index j, conditioned on the set of tokens being equal to a particular sequence of tokens from steps 0 to L, and conditioned on our the other variable C that denotes which component we're talking about, which, remember, just denotes the choice for the sets of values used in A and B that determine the dynamics of the sequences. Okay, so how do we make this useful? You see, the way these sequences work is that they are, well, they're generative, right? And they're recursive, because as the sequence gets generated, we can update this posterior probability as to what hidden state the system is in, because as more tokens flow in, we can update our beliefs. So this sounds very much like a Bayesian update, and that's basically what it is. So I'm going to write this process down using Bayes' theorem. And I'm not sure if I'm going to remember how to do this because it's quite complicated. The algebra is a bit testing, but let's see if I can do it. So I'm going to start with the textbook definition of Bayes' theorem. I'm going to start with the probability of the state L plus 1 being equal to J, just like I've got here. I'm going to condition on the sequence of tokens from 0 to L, and I'm going to condition on C, and I'm just going to use this shorthand now. Let's see, is that correct? Yeah, so, okay, no, I know why I'm getting confused now. So the way to make this actually useful is to decompose it. We need to, because you see, we need to make a prediction about the hidden state at step L plus 1, conditioned on the sequence up to L. But it's going to turn out to be very helpful to write this down in such a way that we separate the token at the Lth position from the preceding tokens that run from the first L equals 0 position up to L minus 1. And it will become clear when I write it down in the textbook form of Bayes' theorem. So this is clearly a posterior probability over the hidden state conditioned on the existing tokens and the component that we're looking at. So I'm going to write it down as just the usual product of the likelihood times the prior, and I'll try and rationalize it. So we've got, so we've got our likelihood here. So this is all about doing a prediction on the Lth token. So like in Bayes' theorem, we start with the posterior with the data, as it were, as the condition variable, and in the likelihood it gets inverted. So this is the token is now the query variable, and the hypothesis is going to be the hidden state of L plus 1 being equal to J, and the tokens that run from 0 to L minus 1 they're sort of like the background. They're not actually they're not directly relevant. Let me see. Let's see if I can remember why. I think it's the Markovian property. Yeah, that makes sense. Yeah, so I can separate out the dependence. So I can separate out the dependence of x at stage L and the tokens that preceded it, because the token at set L only depends, the token at stage L only depends on the hidden state at L plus 1. The preceding tokens, they don't have any dependence on S of L plus 1, because S of L plus 1 only determines the token at XL. Therefore, the tokens from 0 to L minus 1 are just background information. So by virtue of the Markovian property, I can separate them out. So that's why I'm writing it like this. Okay, so that is our likelihood, and then the prior is just the probability that the hidden states at step L plus 1 was equal to J, not conditioned on XL, but just conditioned on the tokens that precede step L, again as background information, and the choice of component. Okay, and then as normal, I'm just going to set the denominator just equal to the probability of getting the token L, and again I'm just going to condition on that background data with the understanding that it's just stating the conditions under which we're writing down Bayes' theorem. So that was a bit painful. So I'm going to try and write down some clarifying. Well, let's see if I can clarify this a bit. So that is background information. That is background information. And that is background information. So really what we're left with, in fact, I need to say it here as well, that is also background information. So I suppose the way to write this down in a slightly more simple, more friendly textbook form would just be to say probability of S at L plus 1 being equal to J, given the Lth token, which is the one we're interested in, is equal to the probability of getting that token, assuming that the hypothesis is true, that S at L plus 1 does in fact equal J, times the prior probability of that hypothesis being true, L plus 1 equals J, divided by the probability of the data, X. So that should look a lot more familiar, where in its textbook form we've got the posterior, the likelihood, prior, and the data. So that's just the traditional form of Bayes' theorem, and I think hopefully from that perspective what I've written down makes a bit more sense. So here of course I'll use a different colour. So here we have our posterior, this is our likelihood, this is our prior, and this is our data. Okay. Now, the written down like this, we're not quite ready to reach the expression used in the paper, because what we're doing at the moment is we're conditioning on the hidden state L plus 1 in the prior, but what we really need to be doing is conditioning on SL at the step L. So if I just write down the prior, I think I'll deal with it separately in one go. So I've got the probability of S L plus 1 being equal to J, conditioned on the sequence 0 to L minus 1 and C. Again, this is just background information. But what I can do is I can marginalise over the states I, sort of like I did earlier. So I'm just going to write I equals 0 to 2, probability of S L plus 1 equals J, given that the hidden state at step L is equal to I, with component C, multiplied by the probability that the hidden state at L is equal to I, again just conditioning on our background data. So essentially what we're saying here is the prior at L plus 1 can be marginalized over the prior at the previous step, because whatever the previous step, whatever the hidden state was at the preceding step, it must have been one of 0, 1 and 2, which are the the values that the hidden state can take. And so by marginalising over those three states using the index I, we can extract a prior probability that refers to state L by marginalising it in this way. Now, let's see if I can remember the cool magic step here. I think I can. Oh yeah, that's right. Where did I put it? Yeah, I think it's this one. This quantity here is matrix A. If you look here, you can see that that is Aij. And this quantity here is our friend eta. Where have I written eta? Yeah, so this is eta c of x from 0 to L minus 1. And it has an index I because we have this I here. And so I can write it as the sum from I equals 0 to 2 of quantity Aij. Oh, sorry, that should have a C as well. Aijc times eta of C. Yeah, the posterior of the hidden state using the tokens up to step L minus 1 as input. Okay, that's a good stopping point for the prior. The next one is the likelihood. And that is equal to, let's see, let's get our really messy expression of Bayes' theorem back. It's equal to the probability of getting the token XL, given that the state, hidden state, is equal to J, and the and the tokens up to, sorry, I'm just getting lost here, and the tokens from 0 to L minus 1 and C. Now, by virtue of the, let's see, yeah, by virtue of the Markovian property again, I can just write that it's equal to XL conditioned on the on the hidden state L plus 1 and C, but not this, because the Markovian property means that it doesn't matter. It's not there's no causal relationship. It doesn't matter what the value of the tokens up to L minus 1 are. The token XL is only causally affected by the hidden state at L plus 1, and I think I revealed that with the DAG I drew earlier, which again is why I like DAGs. Okay. Now that is also equal to something that we saw earlier. Here it is, which is matrix B. So by looking at, by comparing the expressions here, we can see that actually the likelihood is just equal to B. And we need the C in superscript. Okay. So finally then, if we go back to our expression of Bayes' theorem, and by the way, this whole thing, of course, was just equal to our eta. conditioned on or using the sequence up to 0 to L. And I realize actually I've forgotten to put the index in. So this whole numerator actually has an index, J, corresponding to the index on eta, which I'm going to call J just here. And that's because the index J occurs here. And so there necessarily needs to be, and it's not summed over or anything like that. It's a free index, and so it needs to be referenced here. So let's write down Bayes' theorem, but now let's try to write it down in a compact form that really captures what's going on. So we have our eta, which is the prediction of the hidden state on the basis of the tokens up to that point. And which has 3 components indexed by J, because the hidden state can take one of 3 possible values. And according to Bayes' theorem, it's just equal to the likelihood, which we found is equal to matrix B, times the prior, which is this expression, and I'm just going to write it as such. So it's the summation over index I, matrix A, times eta of C, using the tokens up to L minus 1. And again, we'll just need to divide again by the numerator. So I'm just going to write it in the just the lazy form, basically. I'm not going to expand out. I'm not going to expand it out just yet. But that's our form. Okay, so, and we can bring the B inside the summation. So I can write, well, I'll just write it again. So x 0 to L, indexed by J, and it's equal to, I'm going to write the full summation now with, I'm going to put B inside. So I've got I equals 0 to 2. I'm going to put eta first, because I want A and B to come afterwards, which I'll then identify as T, and the whole thing will make sense. X of 0 to L minus 1, and it's got an index I, and then I'm going to write A, I, and J of C, and we're going to bring B inside that summation. And again, I'll just divide by the same denominator. Okay. Now, I showed earlier, somewhere. Did I show it? Maybe I didn't even show it. Oh, yeah. Yeah, it's this one. T is just equal to A times B. So we can see the indices I, J, J, X correspond perfectly. So actually, I can just write, that this whole thing is just equal to eta with X 0 to L minus 1 times T of C, the T matrix, with XL as its argument. And I've just realized, no, it's okay. We have our J index here, but the J index is now, I need to put the J index on T. Yeah, okay. And again, writing the denominator. Okay, now with Bayes' theorem, the numerator is really just a special case of the denominator. So if I just quickly write it in sort of textbook form, usually the way it's written is the probability of the hypothesis given some data is equal to the likelihood of getting the data, assuming the hypothesis is true, times the prior probability of that hypothesis being true, divided by, now you can write P of X just here, but the other way to write it is just the sum of all numerators, of all such terms that take the form of the numerator, but summed over all possible hypotheses. So we can write probability of X, assuming the hypothesis is true, times the prior for that hypothesis. And so really it's just a partition function. In fact, I should probably use a J there, just to differentiate it. So we want to know the probability of a hypothesis being true, and it's just the partition, that is the amount of probability it occupies, if you like, as a proportion of all possible hypotheses that could be true. So I can now borrow that form and write the same thing. So I'm now going to rewrite this denominator here in the form of this numerator, but it's going to be summed over all possible values of j. So just like I've demonstrated here. So let's go ahead and do that. And why not put the whole thing in brackets? So I'm going to sum over j. Let's go from 0 to 2. And it's yeah, I was summing over I, wasn't I? So okay. Tell you what, let's use a new page. Yes, I've actually messed up the indices there. So what I meant to write was that our numerator is actually equal to, well, okay, so we start with I equals 0. T of C of X, I, J, eta of C, X 0 to L minus 1 over I. So that numerator just turns into this. L minus 1 T of C XL, and it has a J index, and I'm going to divide it by numerator as per the Bayes' theorem expression. Oops. Yeah, so a quick inspection then of the forms. Eta is a row vector, remember, and T is a matrix, and so what we have on the numerator is something of this form, and then on the denominator, let's see, now what have we got? Oh yeah, no, sorry, of course. So it's so it is of, on the numerator, it is of this form, but we're actually just so obviously a row matrix times a row vector times a matrix is a row vector, but we're taking the jth index, so it's actually just a scalar on the numerator. On the denominator, we've got a sum over terms that look like this. So it's, again, it's a row vector, but now we're taking the sum over j, and so that is also just a scalar. So it is just a scalar divided by a scalar. But the way to, no, okay, no, it's not a scalar, is it? It's, yeah, it's a sum. The denominator is still a row vector. Yeah, I remember now. So the denominator can be turned into a scalar by multiplying it by a row vector of this form, 1, 1, 1. So that has the effect of, obviously the matrix product of a row vector with a column vector is a sum of 3 scalars, which is a scalar. The reason for doing that form is it still respects this form here. We're just summing over the j index. So I'm sorry this has become a bit messy, but what it's going to look like is this. So we have our eta of c 0 to L minus 1 with our t vector. We'll take the jth component, and then on the numerator we're just going to do the same thing. But here we're just going to multiply by this column vector. I'm going to denote it with this sort of 1 here, which I know is usually used to indicate an identity matrix, but I'm denoting the column vector 1, 1, 1. So all that's doing is it's summing over the indices of j. And so it's still just the partition function that we had before with Bayes' theorem. We're just taking the probability associated with hidden state indicated by index j divided by the probability of all possible values that the hidden state s could take, summed over the index of j. And just to remind you, that is of course equal to the main object of interest, which is the posterior probability of the hidden state given this token sequence up to 0 to L inclusive, which itself has a j index corresponding to the element being predicted. So I think that's probably a good place to stop. Okay, so we arrived at a definition for the recursive application of Bayes' theorem to update the posterior belief about the hidden state conditioned on the sequence of tokens up to the nth position, and we arrived at this quantity eta as a result. So all of the eta all of the eta posteriors are three-dimensional row vectors because they're expressing their belief about the 3 possible values of the hidden state. And so with a three-dimensional row vector, we can plot all these three-dimensional row vectors in a three-dimensional Cartesian space. But of course, these eta vectors are probabilities, so they have to sum to 1, which means they're constrained. And we get just the usual normalisation condition, 0 to L, summed over j is equal to 1. And so if I plot any one of these probabilities, that probability mass function is constrained to a triangle where the triangle, and let's see, I'm not the best artist, but the triangle intersects with the value 1 on each of the axes, and each axis corresponds to a particular j component of eta. So I'm just, without writing all the extra stuff, I'm just going to write eta 2, eta 1 and eta 0, where the index in subscript just refers to the j, and I'm just omitting all this stuff for shorthand. So what we've actually got is this triangle simplex, which represents the space of possible values where this eta posterior actually lives. So let's say I have a point here. Let's see, I'm probably going to mess this up, but it falls at a particular location. Let's see, what's that going to look like? That's going to look like that. So we have 3 values representing the posterior values of eta. So if we pass 10,000, if we generate 10,000 sequences using the particular component, that is the values inside the matrices A and B that determine the token labeled transition matrix that generates the sequence, we'll end up with a point cloud, a set of points inside this simplex. And if you just look at the triangle straight on, you get these cool plots with certain patterns that appear. And those patterns are, in a way, they're sort of like the signature, the almost like a QR code, I suppose, the visual manifestation of the dynamics of the data generation process, or the belief geometry, which I think is the other way of referring to it, although it's not a terminology I'm particularly familiar with. So that's the data generation process. Now the question is, and really the punchline of this whole domain of study is, can a transformer learn these patterns, and can it, how do I put it? Is it learning these, the fact that there are different components? And so a way to go about that is to build a transformer, and inside the transformer there are going to be these activation vectors. So in the one I've built, there are 3 layers denoted by M, and I'm going to give that indices 1, 2 and 3. There are 10,000 sequences, so I'm just going to, in fact I won't index that for now. So let's just talking about the architecture. We'll have the 3 layers, and I'm denoting that with M, and unfortunately I'm using L to refer to the position in that layer. There are 16 of them because I've used sequences which are 16 tokens long. And so just to keep things clean, all of the sequences I generated were 16 tokens long, and correspondingly there are 16 positions in each layer of the transformer. And so each layer of the transformer is defined by the index M, which says which layer you're in, and then the index L, which says which position in that layer you're in. And for each one of these positions, there is a 64-dimensional vector. And so we might write something like this. So what that means is that we actually have a set of data points where for a given M, that is a given layer, and a given sequence N, so let's say for a given M and for a given N, what we have is a set of data points. So we have the activations at the mth layer and at the lth position, and the corresponding value, the actual sequence that was generated for the cth component not the sequence generated. This is the posterior belief of the hidden state conditioned on the sequence up to the point L. And so there's a correspondence because for each of the L positions in the nth layer, we have a 64-dimensional vector. Correspondingly, at the for the posterior belief at the conditioned on the tokens up to including L, we have our 3-dimensional row vector. So the real data set is these pairs of posterior beliefs and the activations, where each one is a 64-dimensional vector. And so the real problem at hand here is actually just to do a linear regression, which is how you map the activations in the transformer to the posterior beliefs on the hidden state in such a way that, just like we plotted the posterior belief geometry in the simplex here, we can do the same thing with these activations. And by comparing the deterministically generated data sets, the tokens generated using the generalized hidden Markov model, with the predictions as obtained by this regression from the activations, we can compare the theoretical belief geometries with the predicted belief geometries, and that's really the essence of the process by which the model is trained and sort of evaluated. The real essence of the paper and the study itself is the fact that the transformer appears to learn factored representations whereby it can actually identify the component C, although we're not quite there yet, so I'll get to that in a moment. But the regression problem is really just to minimize this quantity. We want to minimize the difference between the observed data points, which is the observed data points as generated using the data generation process, with a waste matrix multiplied by these activations, N and L, and we'll add a small bias term as well, squared. So just standard least squares regression. I think there's a regularizer term as well in the paper, but I can't remember offhand. So I'll just have to look back at that. But ultimately the point is that we can compare the activations inside the transformer by virtue of the correspondence with the position L in the nth layer of the transformer with the data generated conditioned on the tokens up to the nth token. And that's really the essence of the comparison. Okay, so I've spoken quite a lot about eta, which is this posterior of the hidden state conditioned on the tokens, written as follows. I'll just write it out again. Conditioned on the tokens and conditioned on the component C. But now to consider what the model is actually going to be asked to predict. It doesn't know the hidden state, and it also doesn't know the component. And so one of the things that the model is going to be predicting is, I'm going to call it beta, basically just because it rhymes with eta. And it is just the joint distribution over the hidden state and C conditioned on X. And so I'll write it as follows. And so beta, and it's going to have indices J and C, because J and C are now the two unknowns. So if there are two components, like I assumed earlier, and S obviously can have values 0, 1, and 2, then beta is a six-dimensional vector because the joint distribution has 6 possibilities. And so, in fact, actually, given the normalisation condition, there are 5 degrees of freedom because, of course, the marginalisation over the joint distribution has to sum to 1. But 5 degrees of freedom is easily enough to be contained or encoded in the activation vectors inside the transformer, which are going to be something like 64 dimensional. And so that's kind of the precursor to the prediction which I'm going to make. So let me just write down the actual quantity that the transformer is being asked to predict, which is the classic next token given the existing tokens. So that's this is the sort of, if you like, the quantity that's made it into the public consciousness, that LLMs, language models, generally predict the next token as a function of the existing tokens. But the model doesn't know what the hidden state is, and it doesn't know what component was used to generate the data. So in order to write this quantity down and incorporate the quantity beta into that expression, we're going to need to marginalize over S and C. So I'm going to write this as the sum from C equals 0 to 1 and J equals 0 to 2. And I'm going to write it as, well, I'll just write it as the joint distribution over X L plus 1, S L plus 1, I'm going to set that equal to J explicitly, and the component C, all conditioned on the tokens up to layer, sorry, up to step L. The next thing I can do is now use the product rule to factorize this out and try and recover beta. And so if I just write this out again, I do prefer writing these sums out in a slightly verbose way. So let's T, if I can get this right. Probability of XL plus 1 given SL plus 1 equals J and C and tokens up to L multiplied by the probability of the hidden state at L plus 1 equals J and the component C conditions on the tokens up to L. So like before, because there's no direct causal relationship between the subsequent tokens, in other words, it's the hidden state that determines the next token, rather than the previous token that determines the next token, we can use the Markovian property to just disregard these tokens up to point L, because these tokens don't depend on it, they only depend on the hidden state and C. And so by using that Markov property, we can just disregard this as if it were not written. And if you look carefully, you can see that this quantity here, which is the joint distribution on the hidden state and the component, is just beta. That's just what I just wrote. So I can write that as beta. And because it took me quite a long time to work out this point I'm about to make, but because because it's the token labeled transition matrices that determine the token labeled transition matrices that determine the dependence of the next token on the hidden state and C. This whole quantity is fixed. Because it's the transition matrices themselves are just fixed and characteristic of the component. So there is no variation in this term. And so you can see that what that means is that the probability of the next token is just a linear function of beta. So I'm going to write it as something like A times beta plus C. And so in order to relate this to what the transformer is actually doing, I noticed that I think it was section 4.1. I'm just looking to the side here. I've got my laptop. So section 4.1 in the paper, transformers represent belief state geometry in their residual stream. It was stated, it's also interesting to note to consider the linearity of the belief state representations we found, and if the linearity is strictly necessary for a network to optimize next token cross entropy loss. So I'm sort of making this prediction with the inadvertent and unintended benefit of a little bit of foresight here. I wasn't necessarily expecting, or I don't think I would have been able to predict that the transformer is likely to make predictions that are linear in their activation vectors, but the similarity with this observation of the linearity in beta was just sort of, it was too obvious to resist it, basically. So what the transformer does, is its logits are, I would say, predicting on the basis of what I read in the paper, and on the basis of the observation that this quantity here is linear in beta, is that the logits are going to be proportional to the layer norm as a function of h, which is essentially a linear function of h. So I'm just going to write that as d of h plus e. And so with that observation that the predicted tokens are linear in beta, and the output of the transformer activation is also, the output, the logits are also a linear function of h, my prediction would be that beta is linearly encoded in h. And for a typical small transformer, typical of this kind of mini projects, the dimensionality of h will be something like 64, which I think is what I used here. And beta, as we've just established, is 6-dimensional with 5 degrees of freedom. And so I would predict that beta is encoded in h.